Okay, so we started exploring biochemistry of carbohydrates previously, and in our last lecture, we looked at the basic units of carbohydrates being monosaccharides, and we looked at classification and nomenclature of the monosaccharides. So we saw that many of these, monosaccharides, the monosaccharides generally, their name ends with the suffix "-ose", that is OSE. And we classify them based on the number of carbons that is present in their structure, so that we are the smallest monosaccharides being the trioses, which had 3 carbons in them. Then we continued 4 carbons, tetroses, pentoses, hexoses, heptoses, all the way to the nonoses. We saw such. Then we looked at stereoisomerism, looking at different isomers of monosaccharides, those that were mirror images of each other. We refer to them as enantiomers. But we could have stereoisomers that were not mirror images of each other. Those we refer to as diastereomers. So you can have these 2 kinds of stereoisomers, those that are mirror images of each other and those that are not mirror images. All of these come together to give you a group of stereoisomers of monosaccharide. Today we'll be continuing with cyclization of the monosaccharides. Looking at the complexity of this course and the fact that it's the first time that you are doing biochemistry, I just think that we shouldn't go beyond cyclization today. Like, cyclization should be the only thing we deal with, and I leave you to assimilate that well before we continue to be looking at the other things like modifications, and then going ahead to look at bringing these monosaccharides together to form oligosaccharides and polysaccharides. So the plan for today is for us to deal with just cyclization, and that will be it. We'll leave it there. So we dive into cyclization of monosaccharides. So far, we've been looking at straight chain structures of the monosaccharides, but in aqueous solution, the aldoses that are having 4 carbons in them and more, and all other monosaccharides having 5 or more carbons in them. When you read your biochemistry books, you read chemistry books, you realize that these structures are generally written in cyclic forms or ring structures. And that is because in aqueous solutions or in aqueous environments, these monosaccharides occur predominantly as cyclic structures. And you know, in the biological system, if you take our bodies, I mean, the internal environment is aqueous. And so you will not have these monosaccharides existing as straight structures, as we have seen from the beginning. But these will be existing in the ring structural forms. And the reason for that is that in aqueous environments, you have an intramolecular interaction that results into the formation of what we refer to as a hemiacetal for the aldoses and a hemiketal for the ketoses. Now, to understand these type of interactions, we need to understand two major kinds of reactions that can occur between an alcohol and an aldehyde. So you have an alcohol and an aldehyde that reacts to give you a hemiacetal, and an alcohol and a ketone will give you a hemiketal. Now, you know that aldoses have the aldehyde functional group in them. It is actually because of that aldehyde group in them that we classify them as aldoses. And the ketoses have the ketone group in them, from which we give the name ketoses. And you can also see, you also see that the monosaccharide structures were having hydroxyl groups along the carbon chain. So monosaccharides are polyhydroxy molecules. In other words, in the structure of monosaccharides, you find a lot of hydroxyl groups in there. So those hydroxyl groups, will act just like the hydroxyl group in an alcohol. An alcohol is having an OH group. And so the many hydroxyl groups that you find in the monosaccharides, can act just like an alcohol, so that within the molecule itself, you have hydroxyl groups, and for aldoses, you have an aldehyde group, and those can interact. The hydroxyl group and the aldehyde group can interact between themselves, just like an alcohol and an aldehyde will react to give you a hemiacetal. The same way, the hydroxyl groups in ketoses will interact. Some specific hydroxyl group will interact with a ketone group in the ketoses to give you the hemiketal. So that means that the structures that we see for the aldoses are actually hemiacetals, and the ring structures that we see for the ketoses are hemiketals. Now let's dive in and look at how this reaction actually looks like. More specifically, how the aldehyde group reacts with an alcohol. So you remember that aldehyde group, which is having carbon, having a double bond with oxygen, and there's a hydrogen bonded on that carbon. Now, the alcohol, intentionally I've written it with red color so that we can trace where each of these parts, the parts of the alcohol molecule, where it goes after the reaction. So we see that first of all, you have the hydrogen from the hydroxyl group of the alcohol reducing the oxygen, which is in that aldehyde group. So these carbon double bond O now becomes an OH, a hydroxyl group, which means we are left with the oxygen and the rest of the chain of that alcohol. So this OR2 now binds onto the same carbon there. So, and that is a hemiacetal. Now you can see, as a matter of fact, this reaction actually continues. More alcohol will go into the formation of an acetal. Intentionally, I have masked that part of the reaction because it is not needed for today. When we continue later to look at the formation of glycosidic bonds between the monosaccharides, then we will reveal that part of the reaction to understand the formation of the glycosidic bonds between the monosaccharides to form oligosaccharides and polysaccharides. So this is a reaction that we're talking about the formation of hemiacetal. Similarly, we have a ketone, and a ketone will be having a C double bond O, and you have two side chains. So the rest of the molecule is on the either side, the both sides of the carbon. And here too, you have an alcohol, and you see a similar reaction where the hydrogen from the hydroxyl group of alcohol goes to reduce the oxygen of that ketone group to have a hydroxyl group, an OH. And the rest of the alcohol residue, the OR3, now binds onto that carbon to give you a hemiketal. So here too, the continuation of that reaction. Intentionally, I've masked that. We shall reveal that later, as I said earlier. So this is the type of reaction that we are referring to, the formation of hemiacetals and hemiketals, which can occur intramolecular, that is within the molecule itself. It isn't that a monosaccharide is reacting with an alcohol, or say you have two molecules that are reacting together. But this is happening within the molecule itself. That is why we refer to it as an intramolecular interaction. So not an intermolecular interaction or intermolecular reaction, no, but this is intramolecular. Within the molecule of the monosaccharide itself, you have this interaction that can result into the formation of the cyclic structures. Now, we will take the example of glucose, which is a common monosaccharide that we refer to. It's an aldose. And you use that to actually look at how the intramolecular interaction of the glucose molecule results into its cyclic structure. We see the straight chain structure of glucose, and I've shaded the aldehyde group at the top. That is on carbon number 1. You have that aldehyde group there. And we see on carbon number 5, there's a hydroxyl group that is also shaded. Now, these two groups are shaded because the interaction that results into the cyclic structure of glucose is between the aldehyde, is between these two shaded groups, the aldehyde group and then that hydroxyl on carbon number 5. Now, you may be wondering, asking, how come it is only this specific hydroxyl group that will be interacting with that the aldehyde group there? Why is it not the hydroxyl group which is on carbon number 4, or the hydroxyl group which is on carbon number 3 or carbon number 2, or even carbon number 6? Why specifically the hydroxyl group which is on carbon number 5 that is having that interaction with the aldehyde group? Now, to understand why that, to answer that such a question, let's take, for instance, right now, wherever you are sitting, wherever you are lying down, wherever you are standing in and watching this or listening to me, at all points in time, you want to find yourself a comfortable position. If at any point in time you feel any sort of discomfort, any form of not being comfortable in a particular position in which you are, you will adjust yourself so that you'll be in the most comfortable position that you can be. Okay, so if that is the case, this actually happens also at the molecular level, so that molecules will always want to find a state of stability, the state at which there will be the lowest possible potential energy. It is at that stage that their molecules are more stable. So to answer that question simply, it means that it is the interaction between the aldehyde group and the hydroxyl group on the 5th carbon, which is forming the most stable of a cyclic structure. That is why it is so that even though there can be interaction between the aldehyde group and any of these hydroxyl groups on the glucose molecule, those structures that will be formed will not be the most stable. And so those structures will always, look for the most stable form to exist. So in the end, you find that the glucose structure, the cyclic structure, will be what we are referring to now. All right. So we intentionally have drawn this straight chain structure, folding it such that you have the hydroxyl group and the hydroxyl group, which is on carbon number 5, and the aldehyde group there, which is on carbon number 1, coming into close proximity. They come, close to each other such that there can be the interaction that we were talking about, the formation of the hemine acetal. So we have the aldehyde group, which is shaded. The hydroxyl group is also shaded. And here we see some nucleophilic attack of the oxygen of the hydroxyl group on the carbon number 1 of that aldehyde group there that is being shown. So the interaction, has started to take place between these two groups. The hydroxyl group, which is acting like an alcohol, and then the aldehyde group there on carbon number 1. Now we move to the right side of the reaction, and we see that two configurations of the glucose cyclic structure can be formed. So we see, first of all, what you can notice is that the hydrogen of the hydroxyl group on carbon number 5 moves to reduce the oxygen that is having the double bond with the carbon on carbon number 1. So you have that hydroxyl group down there. And so the rest of the molecule, the part which is acting as an alcohol, we see that oxygen now covalently bonded onto carbon number 1, just like the reaction we saw earlier with an alcohol and an aldehyde. So then you have what we refer to as a glucopyranose. We will come to this term, the pyranose. As we move on, we'll come to understand why it is called a pyranose. And then you can also take note of the fact that you have the glucopyranose, which is formed on the left-hand side, being referred to as the alpha isomer. So you see the name down there is alpha D-glucopyranose. And you notice the hydroxyl group is facing downwards. But on the right-hand side, where the name is beta D-glucopyranose, you see the hydroxyl group is facing upwards. So that's the difference between the two, the alpha configuration and the beta configuration. You see the hydroxyl group facing downwards in the alpha configuration. And we see on the right-hand side, the beta configuration having the hydroxyl group facing upwards. So Abdul Rauf, Adiza says she cannot hear me. Is she the only one who cannot hear me, or all the others cannot hear me? Adiza, if you cannot hear me, perhaps it is your system. So you may want to check it. Maybe you touched on your speaker or something. Because right at the beginning of the lecture, I confirmed that everyone could hear me and could see the screen. So Adiza, can you hear me now? If you can hear me, let me know. You can write again. All right, so I guess that is a problem with just one person. All the rest, you can hear me and you can see the screen. I'm actually monitoring this with a second device, so I can see that, yes, the screen is showing. So okay. Tawia says, please, sir, what shows that the aldehyde group bonded to the fifth hydroxyl group carbon is more stable than the other carbon atoms? Okay, so Tawia, we can only answer that question if we look at the energy levels of the structures that can be formed if these hydroxyl groups from the other carbons are the ones interacting with the aldehyde group. These days, it's easier to do because of the computational power which is available. We can do some computational analysis, some computational chemistry, where actually we run reactions between the other hydroxyl group, so that we actually can model this reaction. We model it such that we see the energy levels at for each of the possible products that can be formed, and the comparison of it will tell us clearly that the structure which is having the lowest potential energy is the most stable. So we can't just look at it like this and tell, unless we do such an analysis. I mean, computationally, we can do that, and we come to the conclusion that this molecule is what we find because it is the most stable. That is why it is so. I hope that answers your question. Your secondary school chemistry, you were doing some calculation of energy differences for the reactions that you came across. If you remember, you were doing some calculations like that. Okay, so we can continue and take a look at what you were referring to as the alpha and the beta configurations. That's where we ended. So we are zooming in on that. Now you realize that we were talking about straight chain structures much earlier. Before now, we have come to cyclic structures. Now, these cyclic structures are referred to as Haworth structures. Sometimes you see maybe being referred to as Haworth perspective formulas. Sometimes a Haworth projections. Whatever it is, these cyclic structures are named after the British chemist Sir Walter Norman Haworth that discovered these structures and actually won a Nobel Prize in chemistry. So it's a Nobel laureate that won, a Nobel Prize for his work in carbohydrate chemistry. Now, you realize that when we were looking at the stereoisomers of the straight chains, for enantiomers, those were mirror images of each other. And even the other diastereomers that were not mirror images of each other, we were actually looking at the family tree of the aldoses and the ketoses. So those were isomers, all right, but you have those isomers being formed based on the direction of the hydroxyl group, either left or right, on particular carbons. Here, you see, this is a cyclic structure. And so we don't have that sort of the positioning of hydroxyl groups pointing to left or right. But what happens is, first of all, these two, the alpha and the beta configurations, we refer to them as anomers. So this time around, these are not enantiomers. These we refer to as anomers. They are not enantiomers because really we cannot directly, refer to them as mirror images. That cannot be. We can refer to them as mirror images. But what brings about the formation of the anomers is the fact that on carbon number 1, that carbon, which we refer to as the anomeric carbon, there is what we refer to as a mutual rotation of the groups, that is the hydroxyl group and the hydrogen group, which is on that first carbon that we refer to as the anomeric carbon. There can be what we refer to as a mutual rotation. So, it's just coming from the word mutation and then rotation put together to give us that phenomenon of mutual rotation, which is the rotation of the groups, which is on that carbon that we refer to as the anomeric carbon. So that rotation can have the hydroxyl group facing downwards or upwards. So when it's facing downwards, we refer to that anomer as the alpha anomer. And when it is facing upwards, we refer to it as a beta anomer. You will understand the significance of this when we are looking at the type of bonds that form between the monosaccharides to give us the oligosaccharides and the polysaccharides. You realize those type of bonds, either it's an alpha glycosidic bond or beta glycosidic bonds, they have some specificity to some enzymes. So you will come to see the real significance of such when we come to that. So we see these cyclic structures that are referred to as the Howard structures. And we have seen that you can have what we refer to as anomers, which are two different configurations of the cyclic structure, the alpha and the beta anomers. We refer to that carbon number 1. That is the carbon that was having the aldehyde group on it that interacted with the hydroxyl group on carbon number 5 to give us a cyclic structure. That carbon now is what we are referring to as the anomeric carbon. And the process of the formation of the anomers is what we are referring to as mutual rotation. Now, that was an example with an aldose. So let's take a look at another example with a ketose, because we saw two types of reactions. The reaction that was resulting in the formation of a hemiacetal, and then the reaction which was resulting in the formation of a hemiketal. All right, so Rabboni Raboni says, please, can you go over the alpha and beta anomer? Okay, so I've taken the slide back to the previous slide, which is the alpha and the beta anomer. So I was saying that you have the formation of the cyclic structure from the interaction between the aldehyde group on carbon number 1 and the hydroxy group on carbon number 5. Now, the formation of that hemiacetal can be in two ways, so that you have the hydroxy group, which is on carbon number 1, pointing downwards, or you have the hydroxy group pointing upwards. And I mentioned the fact that when you take the straight chain structures that we were looking at before, and you refer to the stereoisomers, we saw stereoisomers that were not mirror images of each other. Those we refer to as diastereomers. And we also saw images that were, or structures that were mirror images of each other. Those were enantiomers. So we had those types of stereoisomers of the straight chain structures. Now, when we come to the cyclic structures, the stereoisomers that we refer to with these cyclic structures are not mirror images. They are not necessarily mirror images of each other in any way, so we cannot refer to them as enantiomers. Well, they are diastereomers. We can say that because, yes, they are not mirror images of each other, but they differ in structure, even though they have the same molecular formula. But the difference we see between these two isomers is just the positioning of the hydroxyl group on carbon number 1. That carbon that was originally having the hydroxyl group on it, the aldehyde group on it. That first carbon that was having the aldehyde group on it, that carbon number 1, the positioning of the hydroxyl group on it is what brings about the anomers, these two isomers that we refer to as the alpha configuration when the hydroxyl group is pointing downwards, and the beta configuration when the hydroxyl group is pointing upwards. And that first carbon we refer to as an anomeric carbon. And we refer to the process of the formation of these anomers as mutarotation. And that is because there can be rotation of these groups. Either the hydroxyl group is pointing upwards or is pointing downwards in this. So what it means is that in a solution of glucose that you're having this cyclic structure, it isn't that you have purely a solution that is having alpha anomers in there, or you have a solution which is having purely beta anomers. You can actually have a combination of these two, the alpha and beta anomers. So that too will actually take you to something which you learned in secondary school much earlier, which was what you refer to as the racemic solutions. So solutions that are having equal number of isomers, the equal number of opposites, or let's say enantiomers in it, the concentration of both are the same. That you refer to as some racemic mixtures, for instance. So yes, you can even extend your thinking to that you can have an equal amount of beta and alpha configurations of these anomers in there, because the molecule is not static, it is dynamic. So you'll be having the rotation ongoing. The mutal rotation is something which will be constant, ongoing in there. Except that, like I said, when we come to the formation of the glycosidic bonds, you see some more significance in there with the alpha configuration and the beta configuration, with some specificity to the enzymes that can break down the oligosaccharides and the polysaccharides that are formed from these configurations. All right, so I hope that makes it clear. It is just about the positioning of the hydroxyl groups, either downwards or upwards on carbon number 1, which we refer to as the anomeric carbon. So Raboni, I hope that is clear. Okay, so we move on to look at the formation of cyclic structure with fructose. And remember, fructose is a ketose. Fructose is a ketose. So just as we looked at the reaction which could occur between an aldehyde group, and then a hydroxyl group, same thing can occur between a ketone group and a hydroxyl group. All right, so Christopher Nuku Tozube says, sir, please, can glucose be in equilibrium between alpha and beta? Yes, that's what I was actually talking about, that you can have what we refer to as racemic mixtures, which I think you did in a senior secondary school, about equal amounts of enantiomers in a solution. So yes, you can have such an equilibrium. You can have such an equilibrium in solution. You can have that. All right, so we're looking at the formation of the hemiketal in ketosis. So we take fructose, a common ketose that we refer to a lot of times. And here we see, the ketone group is on carbon number 2 there. So we see here, to intentionally, we've written that oxygen of the ketone group in yellow, or is it orange? You know how you see it? I think it's clear. Then we have the hydroxyl group there, which is on carbon number 5. Now, we see that we can have two things can occur, can have two things occurring. So what you see is that, first of all, we, apart from this hydroxyl group, which is on the carbon number 5, you will also see the hydroxyl group that is on carbon number 6, also given a different color blue. So that CH2OH is written in blue, so that we can trace the formation of two different types of rings. So you see, this is where the question that was asked by Tawia earlier, that what shows that it is that interaction, the interaction between the hydroxyl group on carbon number 5 is the most stable. So this will actually, this is an example of such. It's an example of such. So we see that the hydroxyl group on carbon number 5 can interact with that ketone group, where you have the hydrogen of the hydroxyl group reducing the oxygen. And in the end, you have this hydroxyl group on that carbon number 2. And we see the rest of the molecule, which is acting as alcohol, that OH group now has a covalent bonding with carbon number 2. Now we see, this is the structure that we see most of the times. This is the structure that we see, which we refer to as a fructofuranose. It's a fructose. So we saw with the aldoses a term, pyranose, and I said we'll come to it to understand. And now we are seeing another term, which is furanose. So we see this is some 5-sided ring structure with this oxygen at the apex there. So you can have this structure forming. And this is what actually you see a lot of times. Then we also have the OH group, which is on carbon number 6, interacting with that ketone group on carbon number 2. And when that happens, you have a 6-sided ring structure, which is looking just like what we saw with glucose. So that you now have what you refer to as a fructopyranose. So you can have these two occurring, but mostly you see that it is the first, the fructofuranose, that you will see because that is sort of the most stable that you'll find. So you'll see that a lot of times this is presented as a furanose. Fructose is presented as a furanose than a fructopyranose. But well, somehow, if you think of it, it's going to be about also the orientation of the positioning of this hydroxyl group on carbon number 2 there. So that if you have this CH2, which will be pointing downwards, then of course the molecule will become more stable. That is because here we're looking at the alpha, but if you have the CH2OH coming down, then there will not be the two bulky groups, CH2OH, up there, that will be having some what we refer to as steric hindrance between these two molecules, these two groups of the molecules up there. So you can have these two that can occur, a fructofuranose and a fructopyranose that can occur, and that is occurring because of interaction between hydroxyl group and a ketone group to form a hemiketal. That reaction which we saw earlier. So I see Juliet is saying that they want a handout. I think I have said this over and over again. I don't do handouts. All these things are inside biochemistry books. If you go to the library, they are there. You can take them and read. There's no point for me to go copying that and pasting it in some book for you and selling it to you. Same way, even if you go onto the internet, even if you just Google these informations, they are there all over the place. So if you want to have a further reading of this, you can always refer. If you take the slides and as a guide, as you look at formation of cyclic structures of fructose, and you go online, you will see a lot of information over there you can read. So it's just a matter of priority. Some of the data which you use to do social media, just make a use of it to read these things. If even if you don't go to the library to take a hard copy book, these things are all over the place. So I don't see the point for me to be copying this, pasting it, printing it, and bringing it to you and be collecting your money for anything. Now, then Kenneth says, please go over the structure of fructose. Okay. So we have not left the structure of fructose. We are still on it. So what I was saying was that in the same way as you saw the aldehyde group in aldoses interacting with hydroxyl group on another carbon, uh, just like we saw the reaction with an alcohol and the ketone to form a hemiketal, we see you can have the hydroxyl group, which is red, interacting with the ketone group in the yellow color. So that hydroxyl group in red gives out its hydrogen that comes to reduce the ketone group to a hydroxyl group. And the rest of the molecule from the hydroxyl group of carbon number 5 now binds onto that carbon number 2. That covalent bond forms there. And so you have a 5-sided ring with the oxygen up there. This is what you see most of the times. And that we refer to as a fructofuranose. You can also have the formation of the hemiketal with the interaction between the hydroxyl group on carbon number 6 with a ketone group there on carbon number 2. So that hydroxyl group is blue. So we see the hydroxyl group blue interacting with a ketone group yellow. So that hydrogen from the hydroxyl group, the blue hydroxyl group, now comes to reduce the oxygen of that ketone group. And so you then have that hydroxyl group on carbon number 2. And we see the rest of the molecule from that hydroxyl group from carbon number 6 covalently bonded on carbon number 2. That gives you a 6-sided ring, which we refer to as a fructopyranose. So you can have a fructofuranose. You can also have a fructopyranose. So these two are possible. They are possible structures that can be formed with the intramolecular interaction between the ketone group and hydroxyl groups in the fructose molecule. So I'm surprised Christopher is now asking why fructose is classified as a ketose, even though it forms a ring structure. It appears you were not in a previous lecture when we classified monosaccharides into aldoses and ketoses. So I think you should go and revise that, the previous slide, to understand why fructose is called a ketose. Clearly, because you find the ketone group. You see carbon number 2. You see the group which is shown in yellow, the double bond O, carbon double bond O. That's a ketone group. That is why it's called a ketose. And you find glucose being referred to as an aldose because it's having an aldehyde group in its structure. So I hope that is clear. So Christopher, kindly go and revise the previous lecture to understand the classification of aldoses and ketoses, because it's very fundamental. So we see that, yes, these two things can occur. Now, but you see the same thing that we talked about, that you can have a beta configuration, alpha configuration. If you look critically at what we just saw, you saw that the hydroxyl groups here on carbon number 1, no, this time around is carbon number 2. Remember that ketone group is on carbon number 2, which means that in fructoses, when you take the cyclic structures, it is the carbon number 2 that becomes the anomeric carbon. So remember, in aldoses, it's carbon 1 that becomes the anomeric carbon, but in ketoses, it is carbon number 2 that becomes the anomeric carbon, because it is on carbon number 2 that you find the ketone group. And we see the hydroxyl groups here in both fructofuranose and the fructopyranose. They are all facing downwards. So that is in alpha configuration. And you can see the name which is written below. It's all starting with alpha. But you can also have the beta configuration. So this is just to show that, yes, a beta configuration can also be formed where the hydroxyl group is pointing upwards. And then clearly here, carbon number 2 is shown as the anomeric carbon. So you can have such a configuration, beta configuration with ketoses as well. Okay, so Nana Beni Kwanzaa says, please, what's the difference between the fructofuranose and the fructopyranose? So it's clear there that you see the fructofuranose is a 5-sided ring. If you look at it clearly, this is a 5-sided ring on which other groups are bonded, but the fructopyranose is a 6-sided ring. It's a clear difference between the two that you can see. And to actually understand that better, let's look at why we call these structures pyranoses or furanoses. So we have 2 organic compounds that we refer to as pyran and furan. So if you look at the structure of a pyran, it's having a 6-sided ring, and you have an oxygen in that ring. You also see furan having a 5-sided ring, also having an oxygen there at the apex of that ring. You see an oxygen that is in that ring structure. So this is pyran and this is furan. Now, if you take the ring structure of glucose, for instance, we see it looks, the ring, it looks just like that of the pyran. So that is why we call it pyranose. Then a furanose, the ring looks just like the furan. The ring is a furan ring. So I hope that makes it clearer for you, Nana Beni. I hope that makes it clearer for you. So it is based on the ring, the cyclic structure itself, which is either taking the form of a pyran or it is taking the form of furan. That is why we refer to them as either a paranose or a furanose. So if you take fructose, we saw that the fructose, the cyclic structure can be a paranose. If it's a paranose, we refer to it as a fructoparanose. And if it is a furanose, we refer to it as a fructofuranose. So I hope that makes it clear, Nana Benyi. We can move on and take a look at just let's make ourselves abreast with these two things. The straight chain structures, we refer to them as Fisher projections, or sometimes that's referred to as Fisher formulas, and that is named after is a German chemist who also won some Nobel Prize in the development of these Fisher projections or Fisher formulas of carbohydrates. So we can place that against cyclic structures, which was developed by Haworth. So that's, yes, if when you refer to either the Fisher projections or the Haworth projections, you know that these two are named after the developers of these structures. Fisher, you can go read much more about these people, Emil Fisher and Norman Haworth. That's who developed these two structures. Earlier before this, you had like some 3D structures which were difficult to actually reproduce or understand, but these two gentlemen, did their best to represent these structures in a 2D structure, like what you see, that you can easily draw on paper and have an understanding of it. So these guys did some great work in the past. So yes, this is to motivate you that you can also come up with something that you'll be recognized with sometime within your country, Ghana, in Africa. You can be a global icon. Nothing stops you. Now there is so much of information and so much of technology that things are much more easier for us than those who were before us. It was harder for them, to study some of these things. Okay, so yes, Tawia, I like that. Yes, you need to have that belief in yourself. So we can also talk about what we refer to as conformational isomers with ring structures. So with a ring structure, so we're taking, for instance, that's the common. So you find these conformational structures with the paranoses. Paranoses who have these conformational isomers, which we refer to as the chair and boat conformers. The chair and boat conformers. Actually, you can there are other conformers that that you see if you go do some research. You find out that you can have other conformers just like half chair conformers and I think even twisted boat conformers, things like that. You find those different kinds. But I mean, at this stage, let's just focus on the chair and the boat conformers. So I think it's even easier to look at this when you see that the ring structure, the glucose ring structure, which we see here, you see that there are some the bonds that are below, they are bold. That as you can see, that's been very bold. So it will make it easier. So that imagine that the carbon that is carrying the CH2OH on it collapses in, and the carbon which is the carbon number 2 that is also having a hydroxyl group on it also collapses in from below. That then will give you the chair conformer. And if for you take, it is only the carbon that is having a CH2OH and the oxygen that is within the ring from the top, if these two should collapse from the top in, that will give you the both conformer. So you can have these two types of conformational isomers, the chair and both conformers in solution. But here again, the chair conformer is the most stable because it is the conformer that makes all the groups that are on those carbons be positioned in such a way that there is enough room, there is enough space around them, such that there is a reduction of what we refer to as some steric hindrance between these groups that are on the carbons. So like I said, yes, you can have others. You can have others like the half chair, twisted bolts, but these are the common ones that we should just stick with at our stage. We should just stick with this. Okay, so I think we can even look much more at the forms of the chair conformers. So if you look critically at this, you realize that this oxygen is up there at the top, but you can have a chair conformer such that the oxygen actually collapses in, whilst it is the carbon with a CH2OH, which is up. So you can have these two forms of conformers. Now, theoretically, you have some vertical line which is drawn through the center of the chair conformers, referred to as the axis. And in relation to this axis, you have the groups that are on the carbon, referred to as either axial groups, which are represented here by AX, and you have groups that are equatorial groups. So axial only means the groups which are parallel to the axis, and the equatorial groups are those that are perpendicular to the axis. And usually when these structures are drawn, you have the equatorial groups being the bulkier groups, because it is in that equatorial positions that there is enough space for bulky groups. This will actually work when you are looking at derivatives or modifications of the monosaccharides, when you are looking at monosaccharides that have some other groups that are bonded on the carbons in place of the hydroxyl groups. And if those groups that are bonding in place of the hydroxyl groups are actually larger, they are bigger groups, then of course there is supposed to be an arrangement of these groups such that the molecules will have enough, the groups will have enough space around them to prevent steric hindrance between these groups. So you can have these different forms of chair conformers in there. Now, another thing, so far, yes, we've seen the Fisher projections, which was a straight chain structure. So sometimes you see that if you take the aldehyde group that is forming a cyclic structure, sometimes it can be just shown with the cyclic, the Fisher projection this way. The first that you see on the left, that is just showing that there is interaction between carbon number 1 and then a hydroxyl group on carbon number 5, which gives you that cyclic structure there. And then what we actually saw, how really the molecule comes out with the Howard projections. You see also cyclic structures, mostly presented in chair conformers. We saw that, yes, you can have both conformers as well. Then there is this last one, which is also referred to as the Mills projections, where emphasis is placed on the direction of the hydroxyl groups which are on the carbon, or the direction of the groups which are on the carbon. And we saw we talk about the meaning of these dash lines, meaning that these are pointing away from us, and the thick lines are showing that these groups are pointing towards us. This last one is referred to as the Mills projection. Not enough information is on these, but it's also one of the ways. If you're looking at the cyclic structures of monosaccharides, you come across this. So these are some common forms or common formulas of cyclic structures of monosaccharides that you come about. So Prince is what the first one. So I was just saying that you have the Fisher projection, which we saw as the straight chain structure, that sometimes you see that the ring structure is shown this way, just to show that there is a cyclization in that molecule from carbon number 1 and then carbon number 5. So it can be shown that way. But really, this is not what occurs in solution. We have seen what really occurs already. So, but this is just a representation of it, the cyclization. So that cyclic structure sometimes is written this way. But the real thing which occurs is what we have looked at, which is the Howard projections. And we can have, different conformers. Actually, if you take the Howard projection itself, which is the second one, that is referred to as a planar conformer, like it's on a plane. So it's a planar conformer. Then you have a chair conformer. We saw that, yes, even with a chair conformer, we can also have a boat conformer and some other conformers as well. But we have stuck with just the chair conformer and the boat conformer. Then I'm saying this last one is also another way that you may come across, which is referred to as the Mills projection. But not so much of information is on it. But you will see some of these structures where the emphasis is placed on the direction of the groups which are on the carbon. so that the dash lines here show that these groups are pointing away from us, and the thick bonds are showing that these groups are pointing towards us. Okay, so I think this is where we can end. And if you have any questions, any contributions, I'm monitoring the chat, so you can write in there. And if you want to speak to, you can raise your hand, and I will allow you to unmute yourself, and then you can speak. So the floor is open. If you have anything to say, you can raise your hand. I will allow you to unmute yourself. And if you have any question that you want to write in the chat too, I'm monitoring it. So if you write, I'll see it and I'll respond to it. All right. The floor is open.